G'day, John here. Welcome to Applied Proxy tutorial, helping you understand the impact of uncertainty in data and simulation. In the next few minutes, I'm going to teach you how to use Monte Carlo quadrature to compute statistics that quantify uncertainty in the predictions of a model. Specifically, I will teach you how to use Monte Carlo to estimate statistics of a model, such as its mean and variance. I'll also show you that Monte Carlo estimates of statistics, called Monte Carlo estimators, or MC estimators for short, are random variables. That is, even for the same model, their value changes each time they are constructed. And finally, I'll teach you how to quantify the variability of these Monte Carlo estimators using the mean squared error. Let's start with a simple example, specifically a function f that maps a d-dimensional multivariate random variable z to a scalar. A simple 2D function is given on the center of the slide. Given a probability density function pi for the random variable z, we can use Monte Carlo quadrature to compute statistics such as the mean mu and variance sigma squared. At a high level, any statistic can be computed using Monte Carlo quadrature with a simple 3-step procedure. First, we randomly draw samples from the joint density of the random variable z. Second, we evaluate the function at each sample. And third, we compute the statistic by the appropriate formula, which will involve summing over each evaluation of the function. The formula for the mean is given on the left, and the formula for variance is given on the right. In this tutorial, and those that follow, I refer to these Monte Carlo estimates of a statistic as Monte Carlo estimators, and will denote them Q. On the previous slide, you may have noticed that Q is written as a function of Zn. This is because the values of an estimate depend on the exact sample set Zn used to build it, even for the same number of samples n. The two rows of the graphics on this slide illustrate this point. The top row displays the one set of samples drawn randomly from the PDF of Z and their corresponding function values. The mean and variance computing using these samples is shown on the far right. Similarly, the bottom row uses another set of samples drawn randomly from the PDF of Z. The mean and variance computed of these samples is different to the first. This means that Monte Carlo estimators are random variables, that is, their value depends on the samples of Z used to construct them. On the previous slide, I showed two different values of a Monte Carlo estimator obtained using two different sample sets. The plot on this slide shows the histogram of values of another estimator using 1,000 different sample sets. The mean of this histogram is equal to the true mean of the function. Unfortunately, it is hard to say much theoretically about the accuracy of any single realization of an estimator. However, we can make statements about how accurate the estimator is on average. For example, the average of an estimator taken over realization of the data is equal to the exact value of the estimator. When this property holds, the estimator is said to be unbiased. Proving an estimator is unbiased is straightforward. As an example, consider the expectation of the mean estimator. First, take the expectation of the expanded form of the estimator. Second, use the linearity of the expectation operator to move the expectation inside the sum. Third, note the expectation of any single value of a function is just the expected value of the function, which we write as Q alpha. And finally, we sum up each expectation and divide by n to obtain the final result. Monte Carlo quadrature can be thought of as an approximation of the exact integral. However, often we must make a second approximation. Specifically, one may want to compute the mean of f alpha, but only have access to an approximation of f alpha, which I will call f beta. For example, f alpha may represent a quantity computed using an exact solution to a partial differential equation, and f beta represents the same quantity computed using the finite element method. Using such an approximation introduces a bias into the estimator. I'll leave it to the viewer to prove that the bias is the difference between the expected value of the two models, but it's not hard. The last proof has all the components you need. Fortunately, when using numerical models, the estimated bias can be decreased by using more accurate approximations. For example, we can increase the resolution of the spatial mesh used by a finite element solver. For example, the plot on this slide shows a blue histogram of a mean estimator that uses n equals 100 samples of f alpha, obtained by computing the estimator using 1,000 different sample sets. The same plot also shows the orange histogram of a mean estimator that uses n equals 1,000 samples of a computationally cheaper but less accurate model f beta, again obtained by computing the estimator using 1,000 different sample sets. As we saw before, Q alpha is unbiased, but Q beta is not, with respect to Q alpha. The orange vertical line depicting the mean of the orange histogram is not equal to the mean of the blue histogram, represented by the blue vertical line. While ensuring an estimator is unbiased is desirable, bias is not the only property of an estimator that is important. The mean squared error, or MSE, is often considered the best way to measure the quality of a Monte Carlo estimator. The mean squared error is the expectation of the square of the difference between the finite sample Monte Carlo estimator and the true estimator value. After some manipulation, which I leave as an exercise to the viewer, the mean squared error can be decomposed into two terms, the squared bias and the so-called variance of the estimator. When estimating the mean of a function f alpha using a model f beta, the variance of the estimator is equal to the variance of the function f beta divided by the number of samples used to compute the estimator. Thus, the contribution of the estimated variance to the mean squared error can be decreased by increasing the number of samples used, that is n. On the previous slide, I pointed out that the orange estimator is unbiased, but I did not point out that the width of the orange histogram is smaller than the width of the blue histogram. Because we use more samples to compute the estimator, the variance of the estimator is smaller. In an ideal world, if I wanted my estimator to be very accurate, I would set n to be very large and use a very accurate approximation of the function f alpha to construct an estimator. However, in practice, the cost of evaluating a function may be large. For example, the evaluation of some models at a single sample of the input z can take millions of hours. In these situations, the bias of the model used should be commensurate with the variance of the estimator that can be attained without exhausting your computational budget. That brings me to the end of another PyProx tutorial. Hopefully you now know how to use Monte Carlo quadrature to estimate statistics such as mean and variance. You should now also understand the Monte Carlo estimators of random variables, and that the mean squared error is the best way to characterize the accuracy of a Monte Carlo estimator. And finally, you should understand that to build computationally efficient estimators, the squared bias and the variance of an estimator should be equal. See you next time.